Well, hello and welcome to this short exercise on matching quadratic expression to quadratic graphs. There are quite a few ways of doing this. One method you might try first is to consider the coefficient of x. And in this example here, the coefficient of x is -8, and half of -8 is -4. So the line of symmetry is going to be the line x is equal to -4, or x equal to 4 is the line of symmetry. Or we could try differentiation to find the turning point, or we could look at where the graph cuts the x or the y axis. Where it cuts the y axis, x is 0 obviously, and where it cuts the x axis, y is 0. Now, for where it cuts the x-axis, you might need to factorize in order to find where it cuts the x-axis. That might give you an indication of which expression belongs to which graph. Or if you examine the graph and it does not cut the x-axis at integer points, or whole numbers if you like, then that will suggest to me that the graph or the expression cannot be factorized. And the only way you can find the values of x would be to use the quadratic formula. So examine the graph and examine the expression itself. Next slide. Right, now we have these are our graphs and these are the expressions. We're supposed to match these four expressions to these four graphs here. Now, firstly, if we have a look at the constants of these expressions, on here we've got 20. The factor pairs of 20 are 1 and 20, 2 and 10, and 5 and 4. Now, none of these factor pairs add up to 10, which then suggests to us that we cannot factorize expression A in the normal way. For expression B, the factor pairs to give us -10 the factor pair is -3 and -7. And for expression C, the factor pair is -6 and -4, because -6 plus -4 will give us -10. And for expression D, the factor pairs will be 6 and 4, because 6 plus 4 will give us 10. Right, which that means that if we then now examine our graphs, we see that the only graph that does not cut the x-axis at an integer point is graph 4. Graph 4 cuts the x-axis somewhere between -7 and -8, and also between -2 and -3. So it is seem to us, or it is seem to me anyway, that expression A will match graph 4. Okay, so x match graph 4. Now, for expression B, and as I said earlier, B has got a factor pair of -7 and -3, which that means that if you plot this graph, it's going to cut the x-axis at the points 7 and 3, and that's what we got here. So we can say that expression A matches graph B. Sorry, the expression B matches graph 1. Right, expression B matches graph 1. Or we can actually differentiate expression C to give us 2x minus 10. And because that is the turning point, so 2x minus 10 will be equal to 0, which then means that x is equal to 5. So the line of symmetry for expression B is going to be the line x is equal to 5. But we have two graphs with symmetry at x equal to 5. So which is it? What we then do is to substitute x equal to 5 into expression b, and we end up with y is equal to minus 4. And y is equal to minus 4 then suggests to us that graph 1 belongs to expression b. Right. For expression c, if we then differentiate expression c, we get 2x minus 10 and x is equal to 5. If we then substitute s equal to 5 into expression c, we get that y is equal to minus 1, as we got here. Sorry about this. Y is equal to minus 1. So expression c belongs to graph 2, or graph 2 belongs to expression c. Now, having identified 3 graphs and 3 expressions, it then follows that the 4th expression, hopefully, belongs to expression d here. And let's check. If we differentiate expression d, we end up with 2x plus 10, and that gives us x equal to minus 5, which is what we've got here. Now, just to check a bit further, if we then substitute x equal to minus 5 into this expression, expression d, we end up with y is equal to minus 1. So we've now confirmed that expression d belongs to graph 3. And I hope all that makes sense. Please subscribe and please sponsor me. Thank you very much, and bye bye now. Bye bye.